We are looking at a fully autonomous surveillance system. A Turtlebot 3 robot tracks a stationary human figure, navigating toward it without any manual input. The system relies on 4 architectural blocks: the gazebo environment, AMCL localization, a custom navigation stack, and YOLO perception. These modules feed into each other in a strictly directed data flow. Information moves in one direction, from the base simulation up through the perception layer. Notice the navigation component. Rather than relying on the standard Nav2 framework, this implementation uses a custom 3-stage navigation stack written from scratch. When synchronized, these 4 blocks form a closed-loop system. The robot patrols, detects suspicious activity, and investigates entirely on its own. Deploying a distributed architecture like ROS2 comes with a specific constraint. You cannot simply turn everything on at once. The nodes require a precise topological initialization order. If you launch higher-level processes before their foundational data sources are ready, the nodes will outpace the system. They end up attempting to process starved topics that do not yet exist. When this happens, ROS2 rarely throws a loud error or crashes. Instead, it triggers a silent failure. The system looks operational, but the robot simply drops incoming goals and refuses to move. To prevent this, the system must be booted systematically. We start from the foundation, the simulation environment, and build upwards, step by step, until we reach the perception trigger. Because this order dictates the functionality of each subsequent node, the 5-terminal launch sequence must be followed to maintain the signal flow. Terminal 1 launches Gazebo. This happens first because it establishes the base reality of the simulation. Without Gazebo actively running, the robot's physical sensors, specifically the LiDAR scans and the overhead surveillance camera feed, do not generate any data. Once the environment is live, Terminal 2 launches AMCL. This node is responsible for estimating the robot's specific X, Y, and theta coordinates within the map. AMCL relies on an active data stream. The moment it boots, it begins listening to the LiDAR scan and odometry topics published by the simulation. If you reverse this order, AMCL boots up, checks for LiDAR data, finds an empty void, and halts its pose estimation. The simulated environment must generate physical data before the robot can mathematically locate itself within it. With the simulation running and localization listening, Terminal 3 introduces RViz. This is the manual intervention step in the sequence. The custom navigation stack we are about to launch requires a constant stream of data from the AMCL pose topic to function. This image shows the RViz interface. Notice the green AMCL particles around the robot. The user selects the 2D pose estimate tool and clicks the robot's starting location. You must wait for the green particle cloud to cluster tightly, indicating a high-confidence location estimate. Without this spatial anchor, the navigation nodes have no starting coordinates to calculate from, severing the operational chain before it starts. Terminal 4 launches the custom navigation stack. This includes 3 specific nodes: an AI star path planner, a cubic spline smoother, and a hybrid MPC controller. Upon execution, these 3 nodes sit idle. They initialize and wait for a destination coordinate to arrive on their subscriber topics. Terminal 5 brings the final module online. It launches the YOLO vision node, which serves as the trigger for the entire sequence. If you boot YOLO before the navigation stack is ready, you risk a timing failure. Should YOLO immediately detect a target and publish the coordinates, those goal messages will be broadcast to a planner that isn't listening yet, and the data will be lost. The perception trigger can only be armed after the mechanical and navigational pipelines are awake and ready to catch the signal. With all 5 terminals active, we observe the system operating in real time. The YOLO node constantly processes the overhead camera feed. As the human actor moves through the frame, YOLO identifies them and evaluates their pixel velocity, labeling activity as walking or staying. A rule-based decision engine watches this classification. If an actor remains stationary for 5 consecutive seconds, the system flags the behavior as suspicious. At exactly t+5 seconds, the vision node uses a homography matrix to translate the person's exact pixel location into real-world map coordinates, publishing it to the goalpost topic. Looking back at RViz, we see the planner's reaction. It computes a collision-free route, the jagged red A-star path wrapping the wall. This raw path passes to the smoother node, refining the sharp corners into drivable green arcs layered directly on top. Finally, the controller reads this smooth trajectory and outputs continuous forward and angular velocity commands to drive the robot's wheels. Watching this chronological cascade happen in milliseconds demonstrates how 4 disparate modules synchronize into a single autonomous behavior. When building complex robotic architectures, the pipeline will eventually stall. To diagnose these stalls, you can use ROS2 command line introspection tools. Troubleshooting ROS2 requires deterministic debugging. You isolate failures by tracing the signal backward, starting from the physical wheel actuators and checking each link back to the camera. First, you use the command ROS2 topic echo on the command velocity topic. This verifies if the controller is actively calculating and publishing forward and angular velocities. If there are no velocity commands, you move one step up the chain. You echo the goalpost topic to check if the YOLO node sent the target coordinates in the first place. To see the entire system at once, you run RQT graph. This tool maps out all active nodes, allowing you to visualize the connections between the perception, planner, and controller modules to ensure nothing is isolated. When a system stalls, you do not need to guess where the problem is. The data pipeline itself holds the footprint of the failure. By mapping integration errors to their fixes, we build a troubleshooting decision tree. If the planner prints an empty TAC error, verify the AMCL coordinates and goal location. If the YOLO window fails, verify the raw simulation feed using the surveillance camera topic. A common silent failure occurs when the robot receives the goal coordinates, but the wheels refuse to spin. The controller lacks localization data. Go back to RViz and manually reset the spatial anchor with the 2D pose estimate tool. If you encounter package not found errors during the initial workspace build, running raw step install in the workspace root will fetch the missing dependencies. Because this architecture relies on standard topic interfaces, the core navigation and perception logic remains consistent, whether the robot is virtual or physical. This shared software stack allows the same pipeline to be repurposed for real-world hardware.